Hello everyone. In this example problem, we will talk about a two-stage countershaft. Now, this example problem, I believe, is probably going to be the most important one for this week, simply because it's going to give you a very good head start on the project. And as you know, for part A in the force analysis, you need to figure out some forces, some moments, some torques, and the countershaft is sort of the trickiest one to go about analyzing. And this problem basically is, I would say, is the solution to some extent for your part A in the project. So I would be I'll try and be very articulate in my thought process as I go about solving this problem, but I highly recommend that you understand this problem thoroughly um, before you attempt the project. It'd be really helpful. All right, so what we have here is a counter shaft setup, and this shaft is supported by two self-aligning bearings, which means that the shaft is held in place in the X, the Y, and the Z direction, but is free to spin about the X-axis at these two bearings. And the other two components are gears, and both of those gears have a force acting on them, or rather, both these gears are being driven by some external force. And now, since these forces are being applied at a certain angle, you have to resolve this in their respective axes, and you'll end up solving the forces in two different planes. So what you've been exposed to in statics and mechanics of materials is probably just in one plane, which kind of makes things easier, but and you'll just have one shear bending moment diagram. And in this case, you'll actually have two shear bending moment diagrams because you have your forces acting in two different planes. But one will be the XY plane and one will be the XZ plane. And I'll walk you through this in addition to, of course, the torques. All right. So again, I didn't mention this in the previous video, but I will post the notes so you can, walk through it. If you don't want to watch the video and you think you're just good enough with the steps, then I'll post the notes and you can download them, print them, write them down, uh, whatever you want to do as you wish. All right. So what we know from this diagram is, again, we know the diameters of the gears. We know the diameter. We don't know the diameter of the shaft. I don't think we need for the forces. And you know the value of the force, but you only know the value of force A. You don't know the value of the force at C. So that's something we'll have to solve for. And yeah, so FA is 1000 newtons and the shaft is spinning at 1750 RPM. And the first question is, what is the torque on the shaft? Now, one of the major assumptions you'll have to make, and this is an assumption you can also make for your project, is that your shaft is spinning at a constant velocity at 1750 RPM, which means there is going to be no acceleration. And because there is no acceleration, so we know that the torque is equal to the inertia times the angular acceleration alpha. And because there is no acceleration, or alpha is equal to 0, it means that the net torque is equal to 0. Now this is the net torque, which means that not a singular torque on the shaft is going to be 0, but the sum of all the torques on the shaft are going to be equal to 0. So you have two torque inducing components in your system. One is this gear due to this force and this gear due to this force. And if you can see already, both of them will sort of twist the shaft in opposite directions and the torques will cancel out such that the shaft doesn't accelerate anymore. So that's our first part. What is the torque on the shaft? And again, we can make a list of assumptions. So the first assumption I'll make here is net torque is equal to 0. And that's because we have no rotational acceleration. like I said, torque is the inertia times alpha, and alpha is 0, so the torque is 0. Right, then again, this is the net torque and not the torque on the shaft. It's the net torque due to both the spinning gears. Now it is spinning at 1750, but there is no acceleration, so there's no net torque that's causing any acceleration. So what is actually the torque on the shaft? And for that, we need to know what the force that is being applied on the shaft, right? And now because this is being applied at a certain angle, we can say, okay, let me erase all these arrows. We can resolve the force Fa into two components. One is along the z-axis, and this is Fa sine 20, and we have along the y-axis, which is Fa cosine 20. Similarly, we have Fc sine 20, and we have Fc cosine 20. And if you notice, Fa sine 20 and Fc sine 20 both pass through the center of the shaft, which means that it doesn't really cause any torque, but Fa cosine 20 and Fc cosine 20 are both torque causing forces. So the only force that actually induces a torque is the cosine components of both the forces, and that's very important to know. We call these kind of forces the tangential force on the gear. So I'll say this is Fc tangential, this is Fa tangential, and the force that goes through the center of the shaft is the radial force. So I'll call this FAR and FA radial. Again, these are just the variables I'm going to use through the problem instead of writing cosine 20 every single time. Okay, so the torque is simply going to be the tangential force multiplied by the distance between the center of the shaft and the force that's being the perpendicular distance. So this distance here, which is the radius. Right, similarly here, it's going to be the radius. So in our case, because we can solve for the torque either using Fa cosine 20 or Fc cosine 20, but because we don't know what Fc cosine 20 is, we can just use Fa cosine 20. So Fa cosine 20, right, this is again in pounds, times the radius, which is 50 millimeters, divided by 2, and Fa is 1000 newtons. The torque on the shaft is 23.5 Newton meters, and then box your answer. So if you have several subsections and each of them require a different value, because we will grade all of these problems online, it's more helpful if you were to box your answers. That way we know exactly where to look. Because if we can't find your answer and you've hidden it somewhere on the page, then we'd probably miss it and not award you the full points, even if you got it right. Okay, so that is basically the torque on the shaft. And let's find Fc while we're at it. And the way to do that is, again, we could have solved this using the values at A or C, right? I used the values at at A to solve it. But if I were to simply do the net torque, the sum of the torques about X are equal to 0, then I can say that torque A, which is spinning it in one direction, minus the torque at C, which is spinning it in the opposite direction, is equal to 0. So the torque at A is equal to the torque at C, right? And so the torque at C is equal to 23.5 Newton meters. And simply because of that, we can say that, okay, we know that torque C is equal to the tangential force at C times the radius at C. This should be radius at A. And this over here from our diagram is just the cosine component of FC. So FC cosine 20. We know TC, we know RC is 24 millimeters divided by 2. And so FC is equal to 2083 newtons. Okay, so we know FC and we know FA, and it's going to be helpful when we have to draw the bending moment diagrams later. Part 2, power. So the power, now that we have the torque, we can solve for if we know the rotational velocity in radians per second. Right, so the torque is something we know, and we don't know the rotational velocity. But in radians per second, but we do know it in RPM. So we can say that omega is equal to 1750 revolutions per minute. And if you remember the conversion from the first video, it's simply 2 pi over 60, which gives us 183 radians per second. So W dot, this is a separate problem, W dot is equal to T times omega, which is 23.5 Newton meters multiplied by 183 radians per second. So the power, again, this is all in SI units, so the solution should be in watts because I'm also using meters instead of millimeters. I end up with 4,300 watts, which is the same as 4.3 kilowatts. So this is the power. Okay, so now that we have the power, part 3 asks us to sketch the torque diagram of the shaft. So what exactly is a torque diagram? So similar to shear and bending moment diagrams that you did in 306, a torque diagram is basically asking you for the value of the torque as you move along the shaft, right? So let's look at our schematic. So as I move from the origin along the x-axis, what I notice is there's going to be points where the shaft is spinning freely and at points where it's actually being twisted due to torques being on either side. So like I said earlier, these are self-aligning bearings, and these bearings allow the shaft to spin freely about the x-axis. So as I go from the origin up until, for 45 millimeters up until I reach the first gear, there is no component or no restriction for the shaft to spin, or there is no torque being imposed. It spins freely, right? It's as if in the rotational sense there is no component at D. So however this gear spins, this shaft spins with the same speed or with the same amount of effort, which is none. And there's nothing holding it back. Now, if I had a component that was twisting it back, then there would be some torsion in the beam here, and that is basically saying that there is some torque being induced in the shaft. So from 0 to the first 45 millimeters, I have no torque. So this here Okay, so we have first 45, and then it's the next component is 30 millimeters away, and then 20. All right, so for the first 45, there's no torque. Then, as I reach, the moment I reach the gear, there is some torque being induced, simply because between the section here and the second gear here, while both of them, because both of them spin in opposite directions, this spins this way, that spins that way, the beam in between these two, so I think from 75 to 95 millimeters, the shaft is actually being twisted to some extent. So imagine if you had a pen and you twisted it in one clockwise direction on the writing side, and then on the clicker side in the counterclockwise direction, you're effectively twisting your pen. So between that, there's going to be some torsion in the bar here, right, at some value for the torque. And we've already determined what that value is. It is 23.5 Newton meters. And in between those two, we have a bearing, but that bearing doesn't really impose any restrictions in the rotation of the shaft. And as a result, it doesn't impart any torque on the beam in that section. And that beam is only subject to the torque being induced on it from the bigger gear and the smaller gear. So after 45 millimeters, we go up to a certain value, and then we're constant till we reach the next gear. And then it drops again. Now, I can make the claim that it drops again if this is a free end, or let's say on the other side over here, we have maybe another bearing, self-aligning bearing maybe. Then it's again a free end. There is no torque, so it's a free end. But if this were connected to a motor or some sort of a load, then this would actually continue, right? So some output load. And this is and this value here is 23.5. And this is your torque about X in Newton meters. Now it's only going to be one torque diagram because it's only rotation about one axis, which is X, as opposed to a shear bending moment diagram. It's going to be in two directions because you have forces acting in two planes, but it's only rotating about one axis. So we only have one torque diagram. So this is something I don't think you cover in ME 306, Mechanics of Materials, but it's kind of helpful to know where you're going to experience torsion or shear stress due to torsion in your shaft. And this will help later when we're designing stuff and even when we're drawing more circles where we have, a shear stress and a normal stress, and we need to map it to figure out what the maximum stresses could be at that point. So this is the torque diagram. It's kind of straightforward. The only thing is understanding where exactly the shaft is free to rotate and where it isn't. Okay, now in part 4, where parts 4 and 5 ask us to draw bending moment diagrams of the shaft in the XY and the XZ plane respectively. And this is what I think is going to be the most important part. So the first thing we need to do, again, there's a process to drawing these diagrams, right? So we need the bending moment diagrams. So again, the process usually is first draw the free body diagram, right? Then solve the forces, solve for unknown forces. In this case, we have some bearings. Like I said, they don't allow the shaft to move in the X, Y, or Z direction, which means there are some support forces or some reaction forces being applied at the shaft on the shaft at those points, which we need to solve for. So solve for unknown forces, then draw the shear diagram. And as you've seen in 306, if you've drawn the shear diagram, you can simply take the area under the curve and draw the bending moment diagram. All right. So let's look at the free body diagrams. So first I'll solve it in the XY plane, right? So I'm going to erase what I don't need here. Yeah. Okay. So as you can see, there are forces that are being applied in the Z direction and in the Y direction. So we are going to have the XY plane because as we move along the X direction, what are the forces in the Y? As we move along the X direction, what are the forces in the Z? So that's why we have forces in two planes. And in the Y direction, we're going to have, oops, we're going to have some reaction RY and RZ. Similarly, at this bearing, we're going to have RY and RZ, right? But this is at D and D. This is at B and B. And we won't have any forces in the X because there is no external load being applied in the X. So when you take the sum of the forces in the X, if there is no external load, all reaction forces in the X are effectively going to go to zero. Now, if you have a different kind of gear, I think when you get later in chapter 15, we'll come back to it maybe later in the semester, where we'll have helical gears that are where the teeth are angled. It kind of induces forces along the direction, along the length of the shaft. But for now, all forces are in the X and Y direction, nothing in the Z and Y direction, nothing in the X. So we can assume that the reaction forces are only in the Y and the Z direction. So first we're going to look at the XY plane. Right? And so bear with me as I make diagrams here. Kind of is a little bit touchy when I'm drawing straight lines. Okay. So the first thing we want to do is actually figure out what all those forces are at the reactions. But for that, we need to know what all the components of those external forces Fa and Fc are. So first, I'm going to draw the forces here. So we have RD in the y direction, then FA tangential, RBY, and in this direction, FC radial. Now, in order to solve this, we need to solve for the reaction forces, and we already know what the tangential and the radial forces are at the gear because they're just assigned components of known values already. So let's write that down on the side here. So we have FAT is FA cosine 20, which is 1000 cosine 20, which equals 940 newtons. Then we need FA radial, which is 1000 FA sine 20. Or I can also solve this by just taking 940 and then multiplying it or dividing it by tan 20. 1000 cosine 20. Wait, this is sine, sorry. 342 newtons. Then FCT is 2 FC times cosine 20, which is 2083 times cosine 20. That's 1957 newtons. And then FCR, which is FC sine 20. That's 2083 sine 20, or 712 newtons. So instead of writing these variables, I'll just write it out as, so FAT is 940 newtons, and FCR is 712 newtons. Now, if we take the sum of the moments, about D equal to 0, and sum of the forces in the Y equal to 0, I think this is something you can solve for, right? Just pivot it about D, and then clockwise and counterclockwise, put them on either side of the equal to sign, solve for RBY, and then sum of the forces in the Y, those pointing upwards minus those pointing downwards, equal to 0. And you should get RBY is equal to 338 newtons, and RDY, which is equal to negative 566 newtons. Now we have a negative value here, which means that the direction we chose for RD in the Y direction is incorrect. It's actually pointing downwards. So that's something that the math works out by itself. So when you're drawing the arrows in for the support reactions and you don't know which way it's pointing, it's fine to assume a direction and the math will solve for it. But it's very important that you draw in the directions correctly for the external loads being applied. Otherwise, the math won't work itself out. In fact, they'll cancel each other out and probably give you something wrong. Okay. So now I can redraw the free body diagram. Again, this is in the XY direction. I have 566. This is my positive Y, this is my X, and then I have 940. Again, these are all in newtons. Then we have 338 and 712. Right, so now that we have all the forces in the XY plane, let's draw the shear diagram. Right, so this is as we go along in the X. And let's put this in newtons. Now, the traditional way to do this, as we learned in 306, was, okay, let's take the first section until the next force. We have 566, and by convention, we draw V pointing downwards. Then we take sum of forces in the Y. So 566 plus V is equal to 0, or V is equal to negative 566. And then we can take the next section where we have 566, we have 940, draw V pointing downwards, and then we say 566 minus 940 minus V is equal to 0, or V is equal to 374. Now, this is, I think, the method that's taught in 306, and it's probably, and it is right, but it probably take a lot of time to do it. So the way I like to go about doing this is kind of a shortcut method. It works and it is right. It's just less working, and if you get things wrong, then there's no partial. So again, I highly encourage it using this method. And again, and in the moment diagram, if your values go back to 0 in some cases, then you probably did it right anyways. So it's a good way to check it. So how I would go about doing this is I would start from the right-hand side and move along the x-axis. As I start from the right-hand side, I'm going to look at which direction my force is pointing with respect to the positive y-axis. If it was in the xz, I would look at where the positive z is pointing. So in this case, 566 is pointing in the negative y direction, which means I have a negative shear force. Again, it's important that you start off from the right-hand side. If you start from the left-hand side, things are kind of flipped, so that this shortcut doesn't work if you're going from the left. So I would just stick to starting always from the right and probably using this method, if I'm using this method. So 566 is pointing in the negative y, so I start off at negative 566 until I reach this point here. This distance here is 45. This distance here is 30. And this distance here is 20. Okay, so till I reach the next force. Now 940, now I have to displace my line by the same amount that the force is in that direction. So now 940 is pointing upwards in the positive y. So I actually have to increase the value of my shear by 940, which means I have to add 940 to 566, or rather I displace by positive 940, which means I go up by 940, and this value here is 374, which is simply negative 566 plus 940. And now I have to displace in the positive sense by 338 because 338 is pointing in the same direction as positive y. So 374 plus 338, which is 712. And the final force is 712, so it brings me back down to 0, which means I probably did it right. So this is kind of a shortcut method I use, and especially when you're dealing with a lot of these types of problems and you don't want to keep using this method, you could simply just use the shortcut and figure things out. Now, if you have an external shear force that's being applied, which you haven't accounted for, then it's probably better to use this method. But again, for the purpose of this class, we wouldn't, and you can get away with just using this method. At least all the examples I've seen up until now, you can use this method and you should be fine. Okay, so now that we have the shear diagram, we can draw the moment diagram. And we know from 306 that the moment is the integral from point 1 to point 2 of the shear force when integrated with respect to x. And in terms of lines and curves, that means integral basically means area under the curve. If I were to solve this algebraically, it would be m of x is equal to m of x evaluated from x1 to x2 plus some constant c. Now in this case, this is the area under the curve of the shear diagram. And the c here is basically an external moment. And this external moment is, for example, you must have seen beams where you probably add another moment here, right? And what this is going to do is bend the beam in this direction. And because in this case, if you were to have an external moment being applied on your beam or your shaft, then your shaft will not, or your bending moment diagram will end at some positive moment value here, and it won't end at zero. But in this case, we don't have an external moment being applied on the beam, so we know for sure that we start at zero and we end at zero. Okay, so let's draw the moment diagram, and I'm going to do this in Newton millimeters, simply because I can just multiply the slope by the distance and I should get a value that's easy to compute. Or you can do it in Newton meter, you can do it in Newton meters, but then you'll have to divide by 1,000. Okay, so we start off at zero, we slope at a rate of negative 566, right? A straight line or a horizontal line in the shear means a sloping line in the moment. A sloping line in the shear means a parabolic line in the moment because you're integrating, right? So you basically increase the order of x. So we slope at a rate of negative 566 for a distance of 45 millimeters. So that value is 566 times 45, which is 25470 Newton millimeters. And then I slope upwards because it's positive 374 for a distance of 30, which is, so this is 374 to a point, so 25,470 negative 25,470 plus 374 times 30 is 14,250. And then I slope back up at 712 till I reach zero. And if you do the math, 712 multiplied by 20 is in fact 14,250. So your value should go back to zero. And now again, when you're dealing with such big numbers like 25,000, and you will have to round up some of these values when you're calculating them, you might not go back truly to zero, you might go back to 50. But 50 in comparison to 25,470 probably means that you had some rounding error somewhere, and it's totally fine. That as long as you're in the vicinity of maybe 1% of zero with respect to the maximum value, you can safely assume that you truly do reach zero. Okay, and again, this is a good way to check that your shear diagrams and your bending moment diagrams are correct. So this is the bending moment diagram for yx, the yx plane. Now we're going to work on the xz plane. And the way they've drawn it makes it easier to have z this way and x this way. You can do it the other way, but it doesn't matter. However you want to draw z down or pointing upwards, but the values for your moment diagram should be correct, negative or positive, because that tells you whether your shaft is in compression or at tension at that point. Okay, so what I will do, I would suggest you pause the video right now and take some time to follow the same procedure for the XZ plane and try to draw out the shear diagrams, solve for the forces, draw the shear diagram and the bending moment diagram, and see whether you get the exact same values that I do. So pause the video right now, try it out, and then come back to the video. Okay, so you must have paused it. If you haven't and you just waited for me to go silent, that's up to you. All right, so let's look at the free body diagram for the XZ plane. We have Again, you can draw this in any direction you want, the reaction forces, as long as you're consistent with the direction of your external forces. So RdZ pointing in the negative Z, FA radial pointing in the negative Z, the reaction at B in the Z direction pointing in the negative Z, and FC tangential pointing in the positive Z. And based on the values we calculated earlier, right, we need FAR and FCT. So these two. So I'm just going to erase and substitute. So FAR is simply 342 and FCT is 1957. And then again, using sum of moments about D equal to 0 and sum of the forces in the Z equal to 0, I get R B Z equal to 2,274 newtons and R dZ equal to negative 659 newtons. So I'll redraw the free body diagram. The arrow's in the right direction. Z is pointing downwards. X is pointing across. We have 659 in the positive Z because it's reversed from my initial direction. So 659 newtons, 342 newtons, 2,274 newtons, and 1957 newtons. So now that we have the forces in their respective direction, we can use the method you mentioned earlier to draw the shear diagrams. So we have our axes, the shear in newtons, right? Again, starting from the right-hand side, we have 659 pointing in the same direction as the positive Z. So even though this is pointing downwards, in relative to the coordinate system, it's pointing upwards, or rather in the positive sense. So this starts off at 659. And let me draw my reference lines. So this here is 659. And then I get displaced in the negative Z by 342, which means I have to go down or negative shear by 342. So that's 659 minus 342, which is 317. And then I go in the negative Z again by 2274, which means I subtract 2774 from 317, which takes me down to negative 1957. And that makes sense because then I get propagated upwards or displaced by 1957 due to that force at the end at C. So this is the shear diagram for the XZ plane. And using the same method we did for the XY plane, we can draw the bending moment diagram. So this is our bending moment. Again, I'll do it in Newton millimeters. Right. So first we have 659 for, again, these are the distances, 45, and these are all in millimeters, 30 and 20. So we have 659 times 45 in the positive. Oops. No, I need more space. So this is 659 for a distance of 45. The product is 29655. And then again, I'm still positively sloping, but with a less steeper slope, which is 317 for a distance of 30. This here is 317, and that new point is 39,165 Newton millimeters. And then I slope downwards by 1957 for a distance of 20. And if you multiply 1957 by 20, you should get something close to 39,100 and back to zero, which makes sense because there is no external moment being applied on the system. So there you have it. You have the bending moment diagrams in the XZ plane and the YX plane. So that's part 4. And part 5, and again, for the project purposes, you need to do up until this analysis on all 3 shafts in your speed reducer to determine the bending moments. Okay, so that's part 5. And so this was part 5. So now we'll go to part 6, where we need to figure out what the maximum bending moment is. Now, just by looking at the bending moment diagrams, at least in one direction, if it was just one plane, you would say, okay, 39,165 Newton millimeters is the highest value because you have 29,000, 39,000, and then 25,000, 14,000. So obviously you would say 39. But because this is acting in 2 planes at the same point on the shaft, things are a little different. So we have the max bending moment. So let's look. So what happens when you have bending moments in 2 different directions? So let's look at, maybe let's take the cross section at C, right? So if we're looking in the XY plane, right, that the bending moment kind of causes something that looks like this. If let's say this is C, right, this value here, the bending moment is 39, 14,000. And then in the ZX plane, you have it also bending, but by 39,000. So if I were to look at the beam from this direction or perpendicular to its cross section, I effectively have something that's bending not in the X. So this is the Y and this is the Z. It's bent if it's effectively bending at some plane in this direction. So if this is its primary cross section, it's sort of bending at some angle, right? Because it's bending in this direction as well as this direction. At some angle, let's say phi, right? So what we need to do is basically figure out what this resultant bending moment is. And it's basically as simple as taking the sum of squares of the moment in the X and the moment in the Y. So what we need to figure out if that sum of squares is the highest at A or at C, because the values could be pretty close. So let's look at some of the moments at A and C. Now I'm choosing only A and C because these are the peak values. Now there's a possibility that the maximum value could be somewhere in the middle, But for the purposes of this class, we're always going to assume that the maximum moment could be at one of the peaks. And there is a possibility that it could be at the middle, and you will probably need like a numerical solver to figure out what the moment is at each point on the shaft. But I guarantee you that, at least for this class, you can just solve for the maximum moment at the peaks and or the resultant moment at the peaks and then choose accordingly, depending on which one's the highest. So moment at A is equal to moment at A in the y direction plus moment at A in the z direction, and the sum of squares. So we have 25,470 square plus 29655 square, which gives us 39,091 Newton millimeters. And if I would do that at C, I would again do sum of squares in the y and z, and I get 39,165 square plus 14,250 square. And that gives me 41,677 Newton millimeters. So from these two values, we can assume that the maximum bending moment is at C. So critical at C. And if you want to know what plane that is acting at, what angle, you can just say that phi is equal to, and because I've drawn it going from the y to the z, I'll have to do tan inverse or arctan moment of z over moment y, and that would be 19.99, which is 20 degrees. And that's pretty cool because what basically happens is you're effectively pushing the shaft at C, schematic here, at C at an angle of 20 degrees. So effectively what you're doing is pushing the shaft at 20 degrees from, in this case, it would be from the Z or the Y. So I think it's just a matter of which way you would write tan inverse, right? You would either get 70 degrees or 20 degrees, either or. It just means that the direction in which this is being pushed is similar to which which direction the external load is being applied. And in our case, that's 20 degrees. And as we get into gears, you will see that that angle is basically called the pressure angle, and it's the angle at which, when you have two mating gears, the force acts along a line that's 20 degrees off from the XY coordinate. So again, if you have any questions about the approach, please post them on the discussion board, and either I will answer it, Dress would answer it, or some of your classmates could answer it if they're confident about it. And again, I will post these notes, and I will post the question just by itself as well. Thank you.